In this video, we will explore the crucial role of synchronization hardware in addressing critical section problems in concurrent programming. We will discuss how hardware support enables the construction of effective synchronization mechanisms. Let's first define what a critical section is. A critical section refers to a segment of code where multiple processes access and manipulate shared resources, such as shared memory. It's essential that these resources are not accessed by more than one process at the same time to prevent data corruption and ensure consistent program behavior. For a solution to the critical section problem to be viable, there are three primary requirements. The first is mutual exclusion. It ensures that only one process can be in the critical section at any given moment. The second is progress, which states that the selection of a process to enter the critical section cannot be postponed indefinitely. And the third is bounded waiting. It sets a limit on the number of times other processes can enter their critical sections before a specific process is allowed to enter its own. Modern hardware provides essential support for synchronization through several mechanisms. The first are atomic instructions. These are special instructions that execute as a single, uninterruptible unit. These instructions serve as the bedrock for building more complex synchronization tools. The second are memory barriers. These are hardware instructions that enforce a specific order in which memory operations are completed. Consider this pseudocode example. A loadx instruction is executed, followed by a memory barrier instruction which ensures that all loads before it are completed. Only then the load y instruction is executed, after x has been fully loaded. One fundamental hardware mechanism for synchronization is the test and set lock, or TSL, instruction. The test and set lock is an atomic instruction that tests and sets the value of a memory location. It returns the original value of the memory location and sets it to true, all in a single uninterruptible operation. Here's how a test and set lock can be implemented and used for mutual exclusion. First, the test and set function takes a Boolean pointer as input. It saves the current value of the target, sets the target to true, and returns the original value. Then, to use the test and set for mutual exclusion, a process enters a while loop that continuously calls test and set on a lock variable. If test and set returns false, the process enters the critical section. After exiting the critical section, the process sets the lock variable back to false. Another essential atomic instruction for synchronization is compare and swap, abbreviated as CAS. Compare and swap is an atomic instruction that compares the contents of a memory location to a given value. If the contents are equal to the expected value, it modifies the contents of that memory location to a new given value. Here's a typical implementation of compare and swap. The compare and swap function takes a pointer to a value, an expected value, and a new value as input. It reads the current value, and if it matches the expected value, the function updates the memory location with the new value. Finally, the function returns the original value. The compare and swap instruction can be leveraged to implement a lock mechanism, facilitating mutual exclusion, and often without the need for busy waiting. Here's how compare and swap can be used for mutual exclusion. Inside a do-while loop, the compare and swap function is called, attempting to change the lock from 0 to 1. If the old value returned by compare and swap is 0, it means the lock was successfully acquired, and the process can proceed into its critical section. After the critical section, the lock is released by setting its value back to 0. Now let's explore the advantages of compare and swap. Firstly, it is more flexible compared to test and set. Secondly, it enables lock-free and wait-free algorithms. Thirdly, it serves as the foundation for many modern concurrent data structures, and it is widely used in real-world systems. Atomic load-linked and store-conditional instructions serve as an alternative to compare and swap, used in architectures like MIPS, PowerPC, and ARM. Load-linked loads a value from memory and marks the location, while store-conditional stores a value only if the memory location hasn't been modified since the load-linked. Consider this pseudocode for load-linked and store-conditional. First, the load-linked operation loads a value from the target memory location. After performing some computation, a store-conditional operation attempts to store a new value to the target location. If the store-conditional succeeds, the update was atomic. If it fails, it indicates that the target location has been modified by another process, and the operation needs to be retried. Let's compare the synchronization primitives we've discussed. Test and set lock is simple to implement and understand, but it causes high contention and busy waiting. Compare and swap is flexible and enables lock-free algorithms, but it suffers from the ABA problem and can be complex to use correctly. Load-linked and store-conditional avoids the ABA problem and is more robust, but it is not available on all architectures. Looking at hardware trends, modern CPUs increasingly support transactional memory. There's also hardware-level support for lock collision and specialized instructions for concurrent data structures. To summarize, hardware provides atomic instructions that are fundamental building blocks for synchronization. Common atomic operations include test and set, compare and swap, and load-linked or store-conditional. These primitives enable the implementation of higher-level synchronization tools, and modern hardware continues to evolve with transactional memory and other advanced features. These hardware synchronization primitives are used to build mutex locks and semaphores, lock-free and wait-free data structures, concurrent programming libraries, and operating system kernels. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.